Hello. The most recent thing we learned about was the chain rule that allowed you to take the derivative of a function of another function. And we're going to use that to learn to differentiate implicit functions. And all that means is that instead of the equation being solved for one variable in terms of the other, so you have y equals an expression that has x in it, the variables are going to be mixed together in the equation. So, for example, x squared plus y squared equals 4. Now you may recognize that as the equation of a circle with its vertex at the origin and a radius of 2, because the standard form for the equation of a circle is x minus h squared plus y minus k squared equals r squared. But we want to differentiate this with respect to x. Well, when we have a term that just has x in it, we're going to do it the normal way. But when we have a term whose variable is not the one we're differentiating with respect to, then we need to apply the chain rule. We differentiate the y the way we normally would, but then we have to multiply it by the derivative of y with respect to x. Then, after you've finished it all, you solve for dy dx in order to answer the question. So the first part of this, again, I'm just going to rewrite what we started with. X squared plus y squared equals 4. I'm going to take the derivative of the entire equation. A lot of people forget about taking the derivative of this other side. When you're taking a derivative, you do take it for both sides. It's just normally y is by itself, so that side becomes dy dx. So we're differentiating with respect to x. So when we see x squared, that's just x to a power, so we apply the power rule and we get 2x. Now we're taking the derivative of y squared. Well, looking at this, it's a power, so I get 2y, but since I'm differentiating with respect to x instead of y, I also need to multiply this by dy dx. When I'm doing this, I usually just write it as y prime because it's easier to carry along in the problem. And then on the other side, the derivative of a constant is 0. So now I have an equation, and in that equation I have y prime. So I want to get y prime by itself. So I would subtract 2x from both sides, and that gives me 2y times y prime equals negative 2x. And then I would divide by 2y on both sides, and that gives me y prime, which is the same as dy dx, equals, and this reduces to negative x over y. So now this part of the question asks me to find the equation of the tangent line to the circle shown at the point. So that point is the point where x was 1. So I need to do two things. Since I'm trying to find the equation of a line, I need a point and a slope. Well, to find the point, I take my original equation and I substitute 1 for x and solve for y. So I'd subtract 1, and that gives me y squared is 3, and then I'd take the square root of both sides, and that gives me y equals plus or minus the square root of 3. Well, the point they showed is in the first quadrant, so it's the positive square root of 3. So my point is 1 square root of 3. Now for my slope is dy dx. So I'm evaluating dy dx at the point positive square root of 3. So that's going to be negative 1 over the square root of 3 for the slope. So my equation of my line will be y minus the square root of 3 equals negative 1 over the square root of 3 times the quantity x minus 1. Or if you'd rather have it with y by itself, you get y equals negative x over the square root of 3 plus 1 over the square root of 3 plus the square root of 3. And you could rationalize those, but that's basically the whole idea there. So When you're differentiating an equation that is implicit, which means the variables are mixed together, if it's the variable that you're differentiating with respect to, you just do it the normal way. But if you're differentiating with a different variable, then you do it the normal way, but then you have to multiply it by the derivative of that variable with respect to the one you're taking the derivative with respect to because of the chain rule. So here's a second example. Y cubed minus xy equals negative 6. They want us to find dy dx, and then they want us to find the slope of the line tangent to the curve when x is 0. They're not asking us to find the equation, just the slope. Okay, so they want to find dy dx, so I'm differentiating with respect to x. So I see y cubed. Well, if I was just looking at y cubed, that's a power expression, so I apply the power rule. But since this variable isn't the x that I'm differentiating with respect to, I have to multiply by y prime, or dy dx, minus. Now here's where it gets a little bit trickier. This is a product, so we're going to have to use the product rule. But while we're using the product rule, we're also going to need to use the chain rule. So this subtraction is in front of the product, so I'm going to put a set of parentheses to contain the entire product rule part of it. So the derivative of x is 1 times the other function y. Notice I didn't take the derivative of y, so I don't need to put y prime there. Plus the derivative of y was 1 times y prime, so that would be y prime times the first function, x. And then on the other side, the derivative of a constant is 0. So distributing my minus sign, I have 3y squared y prime minus y minus xy prime equals 0. I'm going to get all the terms that have y prime on one side and all the terms that do not have y prime on the other side. So I'm just going to add this y to both sides. Cancels out. And then I'm going to factor the y prime out of these two terms. So I get y prime times 3y squared minus x equals y. And to solve it for y prime, I divide by 3y squared minus x. So dy dx is y over 3y squared minus x. Now to find the slope of the tangent line when x is 0, well, first I have to figure out what is the y coordinate when x is 0, because my derivative has both x's and y's in it. So there's my original problem. I'm going to put 0 in for x. I get y cubed minus y equals negative 6. I'm going to move the 6 over to get 0 on one side. Now this isn't a very straightforward problem. You could try to factor it by using the p's and q's and all that stuff. I'm just thinking for a second. 8 minus 2. I can see an answer right away. If y is 2, 2 cubed is 8, minus 2 is 6. Well, no, plus 6 would be 12. So I'm going to use the calculator to find, whoops, I'm going to use the calculator to find the solution of that equation. So, I believe I still have it up here somewhere. Nope. Email. Okay, so I'm just going to use x's because that's what my calculator uses, and the x coordinate will be the same as the y coordinate here. I'm just solving the same equation with a different variable. So I'm going to go to my y equals list, and I'm going to put in x cubed minus x plus 6. And then I'm going to graph it and find its zeros. So I'm going to start with a standard zoom 6. And it looks like it only has one 0, and it looks like that 0 may be at -2. So if we go to second calc, because remember, whenever you want a number about a graph, you go to there, and we're looking for the zeros, so I hit number 2. And then I need to go to the left and hit enter, to the right of my 0 and hit enter, and as close as I can get to it and hit enter, and yes, my 0 is at x equals -2. Now remember, x was y here. So this is true when y equals -2. So our point is 0, -2, and to find the slope, we want to evaluate dy dx at the point 0, -2. So that's going to be -2. I'm just taking the equation I had up here for dy dx, that y over 3y squared minus x. So -2 over 3 times -2 squared minus 0 is -2 over -2 squared is +4 times 3 is 12 minus 0 is 12, which is -1/6. So that would be the slope of the line tangent to that curve at x equals 0. I believe that's it. Oh, here we got another one. All right, so here we have another equation that involves both x's and y's, and we just want to find the derivatives. So for this one, the natural log, we're finding the derivatives with respect to x. So natural log of x, the derivative would be 1 over x. And since I'm differentiating with respect to x, I don't need to apply the chain rule. Plus, the derivative of the natural log of blob is 1 over the blob times the derivative of the blob. Since that's a power function, that would be 2y. But also, since it's not x, I'd have to multiply it by y prime. And then the derivative of this constant is 0. So I can simplify this by canceling this y with one of those two y's. Then I'm going to subtract the 1 over x from both sides, because I want to get the y prime terms by themselves. So now I have 2y prime over y equals -1 over x. To get the y prime by itself, I'm going to multiply by y over 2 on both sides. So these cancel, and I get y prime is -y over 2x. And remember, that's just another way of saying dy dx. When you get more than two variables, then you really have to start writing it this way all the time, because you won't know which derivative you're taking it with respect to if you just put prime. For this one, again, arctangent, that's one of our inverse trig functions. And we learned that the derivative of arctangent of x was 1 over x squared plus 1. So it's handy if you have that memorized. If you don't have it memorized, then you'd need to derive it. But we'll just stick with having memorized it. So, derivative of arctangent of blob is 1 over the blob squared plus 1 times the derivative of this blob. Well, that blob is a product, so I need to apply the product rule. The derivative of the first function is 2x times the second function, so I'm doing the function, not the derivative, so no y prime, plus the derivative of the second function would be 1 times y prime, so y prime times the first function, x squared, equals, now on this side we don't just have a number this time, we have another product. So we have to apply the product rule again. So the derivative of the first function is 1 times the second function is y squared, plus the derivative of the y squared is 2y times y prime, again applying the chain rule, times the first function x. So let me just clean this up a little bit. we have 2xy plus y prime x squared over the quantity x squared y squared plus 1 on the left, and we have y squared plus 2xy y prime on the right. So I need to separate my terms that have y prime. Well, before I do that, I'm going to multiply by this denominator so I don't have fractions. So I get 2xy plus x squared y prime equals y squared times this. Remember, this is squared, so this would be x to the fourth y squared. So that's going to be x to the fourth y to the fourth plus the 1 times the y squared is y squared plus, multiplying here, I'm going to get 2x to the fifth y to the fifth times y prime plus times the 1 is 2xy y prime. Now I have two terms on the right side that have y prime in them and one on the left side. So I'm going to subtract the x squared y prime from both sides, and I'm going to subtract these two terms from both sides. So this cancels out, and on the left I now have 2xy minus x to the fourth y to the fourth minus y squared equals, now over here, these canceled out, and I'm going to factor out the y prime here, so that leaves me with 2x to the fifth y to the fifth plus 2xy minus x squared. So to get y prime by itself, I divide by this whole mess. So these cancel. So I get y prime, which is the same as dy dx, is, now I'm going to try to simplify this a little. In the numerator, I have a common factor of y. So I'm going to pull that out, and that leaves me with 2x minus x to the fourth y cubed minus y. In the denominator, I have a common factor of x, so that leaves me 2x to the fourth y to the fifth plus 2y minus x. And that, I believe, is as simple as that one gets. Okay, last question. Okay, the equations are getting messier and messier, aren't they? We want to find the equation of the tangent line at the specified point. Now remember, that means not only do we have to take the derivative of this, but we need to plug this point into the, well, actually, they gave us this point, so we don't have to plug it into the original equation because we already know the y-coordinate, but we'll have to plug the coordinates of this point into the derivative to find the slope. So first we differentiate implicitly with respect to x. So this is just going to be 3x squared. Here we have a product. I'm going to keep the 5 out of it. So derivative of x squared is 2x times the second function y, plus derivative of y is y prime times the first function x squared. 2y squared, the derivative would be 4y, but again, since we're differentiating with respect to x, and this isn't x, we have to multiply by y prime. Equals, derivative of 4y is just 4, but again, since this is y and not x, I have to multiply by y prime. And the derivative of the constant is 0. So you didn't have to keep the 5 separate. You could have combined it in this. Either way, I'm going to go ahead and multiply it through now. So I have 3x squared plus 10xy plus x squared y prime plus 4y prime equals 4y prime. So I need to move all the prime terms, y primes to one side and everything else to the other side. Well, all of these are already on this side. So I'm going to subtract these two. So I'm going to subtract x squared y prime and 4y prime. So these cancel, and I get 3x squared plus 10xy equals, I'm going to factor the y prime out. So I have y prime times 4 minus x squared minus 4y. Then I divide by the 4 minus x squared minus 4y. And that gives me dy dx equals, on the top I can factor out an x, and that gives me 3x plus 10y. And in the bottom I can't factor anything out, so 4 minus x squared minus 4y. So then I want to evaluate that at the point 1, 2. So the derivative evaluated at the point 1, 2 is 1 times 3 times 1 is 3, 10 times 2 is 20, over 4 minus 1 squared is 1, minus 4 times 2 is 8. So that's 23 over negative 13 would be the slope. So the equation of our line would be y minus 2 equals negative 23/13 times the quantity x minus 1, or y equals negative 23/13 x plus 23/13 plus 26/13 would be plus 49/13.